for attending to this event, and thank you to Sherry for inviting me. So my name is Rosella Arcucci. I'm a lecturer at Imperial College, lecturer in data science and machine learning, where I had the data learning working group. So I'm mainly a data scientist. So a mathematician as, let's say, my master's degree and then PhD in computational in computer science. And then I've been working with a lot of institutions on real world scenarios. So my first postdoc has been with the Euro-Mediterranean Center on Climate Change. And then I've been working with the DSI Data Science Institute at Imperial College since few years now, before becoming lecturer in data science and machine learning. And so behind, obviously, all the questions that I try to answer in my research, there are data. Obviously, we know that we are in the era of the data, but when I say data, what I mean, just to make sure that we are on the same page over the next slides, when I say data, I don't mean just the what we call observed data. So for example, from social media or from satellite sensors, but also data coming from models. For example, computational fluidodynamic simulations and or just dynamic simulations. So data provided from both observations and forecasting models. So why we are interested in those data, what we can do with the data? Obviously, there are a few main aspects that we try to focus on. The first one is learning the dynamic behind the data. When we try to understand a phenomena and we don't have any information about the phenomena, so we just try to understand something using the data. So we try to learn the dynamic behind the data. Also, most of the time in real world scenarios, we have to deal with big data. So to work on this forecasting model using a huge amount of data, then we have to deal with compression, reduction of the data. And finally, when we have this data-driven model, then we work a lot on trying to make the data-driven model stable. Data-driven models are very famous to be unstable if the data you have been using to train them is not a good quality. So we work also on technologies to help the data-driven models to improve the stability and have good forecasting. So I will tell you more about this over the next slides. Just to introduce you why we talk about data learning, so not just machine learning, is because the main point when you try to build data-driven models, obviously you have to deal with few problems. As I said, the dimensionality constraint, data can start being very, very big. Also, obviously, we have noisy data, and this is almost all the time. I could say all the time, not almost all the time. And finally, another very important problem is when you have low quality data. We say low quality data when, for example, you have data representing one of the variables of your system, but you want information on another variable. So you don't have very representative data, but somehow related to that. So in order to face all these problems together with a reduction of the uncertainty, then we combine machine learning model with something called data assimilation. This is the reason why we talk about data learning models. So data learning models are a combination of data assimilation, which is a data science model, with machine learning, so models to train our forecasting problem. So within the data learning group, we have been working on a lot of different applications thanks to the grants that we have for the group. And we have been working on social science, medical application, we will see now COVID, but also geoscience, biology, finance. I will show you just a few examples, and then I will focus on the application to modeling the pandemic. So all these applications, how you put together all these applications under only one umbrella, they can put together under the umbrella of something called Sustainable Development Goals. Now all the companies have to implement Sustainable Development Goals, and the technologies that we implement, so these digital twins, these forecasting model, these methods to clean the data, can be used in some of these goals.
Rosella, just a quick point.
Yeah.
Sustainable Development Goals were actually discussed by Omar in the previous session. I don't know whether you attended that, but yeah.
Yes.
Thank you.
Yes. Okay. Thank you. Sorry, I was in another meeting, so I had to jump on this, and I missed the other talk. But I will watch the recording. But thanks for letting me know. So I have few collaborators within the data working group working with me, and also lots of students. So we are open to project with students all the time. I'm reporting here just students that have finished projects that have they have published the results of their projects, but we have a huge number of students coming to work with us in the data learning group. So just a quick overview on the kind of models that we are developing. All the time we focus on offline and online, depending on if you are in production, so if you are training the model, or then if you have to use that in running time. And depending on if you want more accuracy, what I mean, if you really care about having a good accuracy of your forecasting, or if you don't mind having an approximate accuracy, let's say the solution may be just approximative, but you want something really fast, or both, hopefully. So depending on if you want more focusing on the accuracy or the efficiency, we developed several types of models. I will tell you more about this over the next slides. All these models are developed with a pre-process. So we study all the time from the data, the analysis, we run analysis of the error, we study the distribution of the error, and we always try to focus on the questions behind the data to make the models be able to be used then in decision making. So about the accuracy, let's focus on, let's say, the offline part. So we have mainly two kinds of models which are based on optimal data selection and parameters estimation. So optimal data selection, and this is also important for COVID. I will show you after why. So imagine you have a room, a class, for example, and then you want to collect information from some sensors. One of the questions may be, okay, where should I put the sensor to have most of the information in the room? So I don't know if you're probably you're already aware of that, but considering the airflow within a room, where you put a sensor, the sensor will be able to capture most of the information about, for example, the air quality or not, depending on the position. So how can you do that in advance? Should you put just sensors in the room randomly, or you can understand what is the optimal placement? This is what we have done with this technology based on Gaussian process, mutual information, and data assimilation. So I'm a mathematician, so I can be very detailed and give you all the information, but I will just give you an overview of the models, and then I'm very happy to go into the details in case you have other questions or share with you the papers. So all these models I'm going to show you have been already published. So we have the papers and also the code on GitHub to be run. So as you can see, if you just use a random sensor within the room, or you put the sensor in an optimal placement, you have a mean square error, MSE stands for mean square error, a reduction of the mean square error of, let's say, 3 orders of magnitude. So the forecasting with the sensor placed in a random place gives you a mean square error of 0.17. If you put the sensors in the optimal location, you have a very high accuracy of the forecasting. This is very important to us in some scenarios, like, for example, air quality in a room. just to let you see that the technologies we are developing are completely general. So, for example, that the same technology that we use in an indoor environment can be used in an outdoor environment. So this is Elephant and Castle in London. This is where is the London School. So the university. This is just on the corner, and these are the results of the optimal sensor placement or a random placement. This is a simulation of for simulations of air pollution in a city. Parameters estimation in a completely different scenario. Let's assume, for example, that you want to estimate parameter of an economic model and you want to use data from the cryptocurrency market. Then you have this time series. All these points are essentially time series, can be exploded in time series. So if you want to estimate these parameters, beta and alpha, for example, then how can you learn from the data the optimal values of these parameters? We have done that using data assimilation. We have been publishing quite a few papers about that. And as you can see, the most important part is that when you just set up the parameters, even from historical data in a proper way, but then you try to use the model to make any forecasting, then you have an error which is around 1.4. Anyway, almost on the first order of magnitude. And then if you use the data simulation to estimate the parameters, and then you use these parameters within your model, then you have a reduction of up to 6 orders of magnitude. So very gain in terms of accuracy, a big gain in terms of accuracy. Then surrogate models. So imagine you have your CFD, so your computational fluid dynamic model, which can, for example, be used in this case, still air pollution. It can be used to make forecasting, but it is very slow. So we develop technologies that are able to emulate what a computational fluid dynamic software predicts, but in real time. So this is 4 orders of magnitude faster than a standard CFD simulation. And as I was saying at the beginning, we work a lot on making the technologies stable, so that like a standard data-driven exploded after a few time steps of forecasting, our surrogate models are able to make forecasting for a longer time. We know that all these technologies are computationally very expensive, so sometimes we are not able to do that on a standard, let's say, technology. We have to use a supercomputer, and then to do that, we use domain decomposition, and we so decompose a domain in subdomains. And these are some gains also in terms of energy reduction, so power reduction, when you run a proper algorithm on a supercomputer. So finally, data simulation. I will be quick on this because I will give you more details for COVID about data simulation. So data simulation is these technologies that merge together 2 information in only one output. So imagine you have something which has been predicted by a model and something that has been observed by some real data, so from sensors or from any other kind of information. So you merge together these 2 data, and you have this assimilated data, which is more accurate and reliable of the first 2. This can be done not just for geoscience or medical application, but also, for example, for sentiment of people. I will not focus too much on this because of the lack of the time. And then finally, data learning and surrogate models. So the main question is, we all rely on real data. But the point is, sometimes you don't have data all the time, especially when you use sensors, imagine. You don't have data all the time. Sometimes you have gaps in your observation. So what can you do when you have these gaps? And this question is answered using this technology, which learns how your forecasting model misfit from the observed data, and learning this misfit can be used to predict future forecasting assuming, so without real observation in time windows when you don't have observation. And just to let you see that with this approach, even when you don't have observations, the model works quite well in terms of accuracy. So the blue line is the model which is running without real observations, but with this network behind it. So this can be also used for integration of both geoscience and social media, and we are doing this, for example, in the context of wildfires. So about modeling the pandemic, all these models that have been showing over the past slides are very modular, and they are like very general. They can be used in a lot of different scenarios. So as I said, I've been working with the Data Science Institute for quite a long time. And December 2019, the pandemic was still not a pandemic. So I remember we had China. It was mainly just in China, and we were trying in the DSI, in the Data Science Institute, to collect, some funding to send them masks and other stuff. Very important. We all know now, very important when you are trying to face a pandemic. And then the director of the Data Science Institute at the time said, "No, guys, okay, we can do that, but what we really need to do that now is using your brains to help facing the pandemic." So, and all started that December 2019. And on February 2020, we attended to the first meeting at the Royal Society, when also Ferguson was presenting the first results from the at Imperial College from his research. So we were all presenting what we were starting doing, and together with other companies. And so since that moment, we have been working mainly on several different approaches. So the epidemic models, for us, as I said, forecasting model using data, and then air quality and air flow in indoor environments, and finally vaccination strategies. So I will give you a quick overview of these three main problems we have been facing. So about the epidemic model, as I was saying before, this data assimilation, this technology which is able to merge together a forecasting model, ingesting new information all the time. So using this kind of technology, we have been adjusted, let's say, the parameters of the SEER model, and also a different version of the SEER model, where we also introduced the treated people in the SEER model. Treated people have been implemented just for China, because for China we had the information about the number of hospitalization. I'm talking about beginning of 2020. So at that time, we didn't have this information for worldwide. We just have lots of information from China, and broad information about the number of infections worldwide. So we separated, let's say, China and the rest of the world with the SEER model, and SEER model plus treated for China. And essentially, what we have been doing with this is helping the SEER model to be more accurate in terms of forecasting the peak of the infections, learning the new parameters from the new available data all the time. And obviously, one very important point here, and in case you are interested, I'm happy to give you more details, and the details are provided in this paper. The most important point here is that we are assuming all the time that the data provided by the government are noisy. Not because the government didn't want to provide the real data, but because it was, especially at the beginning, impossible to track the number of infections. So obviously, learning completely from the data, you are learning something which is really noisy. Assuming that the SEER model is very accurate is also a strong approximation. So at some point, we implemented something called, in the context of physics-informed machine learning, And so we balance together the information from the SEER model and from the data in only one integrated model, which was putting together these two information, SEER model plus data-driven model, so model developed from the data. And we have seen in the forecasting, long-term forecasting, an improvement in terms of accuracy in using both, so this physics-informed approach. But why? So why at the beginning we were interested in understanding the peak? Why that peak was so important for us? So we have been doing that because this was integrated in a system able to understand the impact of some mitigation or some suppression. So what I mean, mitigation is, for example, this rule of keeping, this 2 meters distance. And at the beginning, if you remember, at the beginning of 2020, it was like crazy. People didn't really know how to implement that. And also the suppression that may be, for example, the lockdown. So when we developed this tool, that 1.5 years ago, then it has been used to understand the impact. So the impact of some mitigation and some suppression effects in terms of number of infections. And we have been checking the impact of these in both China and European countries like in the UK. So, but when the number of infections, when these, let's say, the population starts to be, when you want to understand how the infection goes within the population in a city, then the number of these movements, the number of variables in the SEER model, the seed vectors of the SEER model start to be very big. So this means that they may be computationally extremely expensive. So imagine that you have, for example, you want to model workers, non-workers, male, female, children. So it starts to be like a number of variables very high. So when we started working on this aspect, so within cities, then we have seen that it was impossible running in a acceptable time this kind of simulation without stable data-driven models, without machine learning models. So we have been working on generative adversarial networks model and recurrent neural networks model. We have published this paper called Digital Twins for Digital Twins for COVID, and it has been published on Neurocomputing, Journal of Neurocomputing. But let me show you a few results. So so what is very interesting now is the execution time in terms of seconds. So the SEER model takes, let's say, 0.45 seconds. So the other models, so the machine learning models takes up to 4 orders of magnitude less, which is very important when then you want to forecast months or at least weeks. And this is in terms of accuracy. You can see that this is the movement of the infection within the room, within the city, sorry. And this is how the model, the SEER model is predicting, and what the AI model is predicting. So this was for the epidemiologic part. Then there is we have been work with the applied modeling and computational group on airflow and air quality in indoor environment. Let me show you why. So imagine, for example, in a room, and the question was, okay, when you have a class and you have students in the class, what happens if a student sneezes and the student doesn't have the mask? So to do that, of course, we can implement airflow simulations, but also to make it more realistic, reliable, especially realistic and reliable, then we have been merging these simulations with real images, real simulation, real observation of people sneezing and coughing. So, and this is how this integration happens. So the background is what a computational fluidodynamic software says. when somebody's sneezing, and then the observation is saying something different, and then you can see the integration. But let me give you a few information about why. Obviously, when you have a fluidodynamic simulation of something, when you have obviously your input data and then your solution. So what we are trying to do here is improving the accuracy of the input data, because the error in the input data propagates to the model on the solution. This is the reason why we are trying to integrate information in the input data in the initial condition in order to have better forecasting. And this is, for example, what happens in a train. This has been a simulation. My group has been working together with the group of Earth Science and Engineering with the for the ramp called ramp task for Royal Society response for COVID. And obviously, this is for the part of airflow and aerosols. But obviously, that one was a person which was coughing and sneezing. But what happens if you just breathe? And then, together with the University of Cambridge, they have been providing data of people just breathing, or even what happens when they have a mask, or breathing, laughing without a mask or with a mask. So what happens? And all this information can be included in the computational fluidodynamic simulation, so you have a better understanding of what is happening in the indoor environment, integrating
Hi,
this
Rosella.
information.
Hi, sorry to jump in. Can I just say that time is pressing, and so if you maybe move towards conclusions, and if there's any questions, this would be a good time.
Okay. And then with the there is the vaccination strategy. Also for that, we have been using neural network, graph neural networks. The main point in the models we have developed is the integration of this data assimilation in the models based on the centrality, and we can see the impact of in terms of accuracy of ingesting real information within the system. Yeah, so I was concluding and just to say that we are happy to share. We have our codes available for you in case you are interested, and we are happy to provide any extra info. And also happy to have you. We are organizing every year a workshop on machine learning and data simulation for dynamic system. You are very welcome to join us. And that's it. Thank you very much for your attention.
Great. I think Tim has a question.
Hi there. Yeah, thanks for that really interesting talk. I'm curious to know, do you think these approaches will replace the traditional models, the epidemic compartment models and things like this in the future?
So not replacing, integrated in.
Okay, so in the sense that people won't be doing just dynamical systems modeling anymore.
Yes, yeah, I think that the use of the data, information from the data will be definitely, yeah. So the answer is yes, not replacing, but even more and more information from the data will be used and ingested in the standard models in the future.
I should educate myself about this a bit more then. Thank you.
Yeah, so Rosella, that was very interesting. So following from Tim's question, you're not trying to replace SIR or anything like that. You're just saying that the data assimilation is a problem, which I agree. There are problems with some underlying models with regard to the data on the networks, or let's say, as you said, various behavioral inputs, like with and without masks, who's inoculated, who's not. So we have problems finding that very granular data on the ground. And you're saying we've got to do things to clean that up before we feed it into the models. Am I right? And then you say, so you have a number of models, and you mentioned the RODA one, the reduced deep learning one. You also mentioned how we could use GANs. So just tell me, which of these fared best? Did you do a beauty contest on the different methods of cleaning on the same problem?
Yeah, so actually we have just published a paper on the Journal of Computational Science called Data Learning. So the name of the paper is Data Learning, Integrating Big Data Assimilation and Machine Learning. And in the paper, we say exactly this. So obviously, depending on the problem, which usually means depending on the question that you want to answer, there is one model which is working better than another. So yeah.
So for COVID, so Rosella, for COVID, obviously you've done a number of different models for data cleaning and assimilation. Which of these worked best? Is there any way of judging that?
So I think that the one working, not say working best, the one that in my heart feels more useful because it's very important is the data assimilation for parameters estimation of the SEER model. Because even in the SEER model, all the parameters, the beta, the alpha that has been modeled to understand, how the blocks are connected. If you make that parameters dynamic and you change the parameters in time, because that parameters are in reality dynamic, because the environment changed, the governments are changing the rules, etc. So that parameters are not static, are definitely dynamic. So learning that parameters from the data and adjusting the SEER model using that new information, that I think is one of the most useful parts for the.
So how would you learn it? And that's the thing, that which of these methods you talked about would do the better job?
Yeah, essentially you solve an optimization problem. So you learn that from the information provided by the government in terms of a number of infections, a number of hospitalizations, number of people in that country, in that city, number of students, and if the schools are open or not. So all this information may be included in this optimization problem that, let's say, minimizing the optimization problem, you have the optimal parameters that you can use for the SEER model, changing that every day, for example.
Okay, thank you.
Thank you.
Can I ask a quick question?
Yeah, of course.
So, Rosella, so you mentioned something about an economic model which looked like a state space model where you are estimating an unobserved variable. What was the application of data there? Because the usual Kalman filters and so on, they can be applied, to infer that beta coefficient that you are showing, right? Which will evolve over time. So what was it? I somehow missed it. What was what was your point there?
So the model was a bar model, and the application was the cryptocurrency market. So especially we have in the paper I was showing, we have experiments for the Ethereum, but any other was the same for us. And so we have been using a variational approach. So both Kalman filter and a variational approach, which is very efficient in terms of both speed and accuracy, to estimate the optimal parameters. So also in that case, similar case, instead of having the parameter static, we have this change of dynamic change of the parameter. As soon as you have new information from the observations, in that case, the cryptocurrency market, then we were ingesting this information in the optimization problem, estimate beta and alpha, give beta and alpha to the VAR model, make the prediction.
Okay, I see.